Okay, so next we are going to discuss uniform circular motion and review it quickly. So uniform circular motion has a net acceleration directed toward the center of the circle. If you recall, we call this centripetal acceleration. Centripetal means center seeking. And the magnitude of that acceleration is the speed squared, v squared, divided by r. R is the radius of the circle. And also it requires a net force acting toward the center of the circle to maintain it. So that force is also toward the center. That's also called centripetal force, that center seeking force. And they, as you can see, these two have the same direction as they should be, right? Because we know that F is equal to MA. And we are saying that F and A points the same direction. So the key things here are that this is a net force. So the centripetal force is the net force. Okay, so this is what you're dealing with. And then that becomes m times v squared over r. Okay, so whatever that centripetal force is along in the direction of x, y, or z, and then you're going to write that down as sum of F. That's going to be equal to mv squared over r. So it's very important that you see the circular path first. So whenever you see circular path, okay, check that. Then you're dealing with a centripetal force and you're dealing with this acceleration. The magnitude is here. So you have to use them and find out what the net force is towards the direction, towards the center of the circle to be able to write this equation. Okay, so my first case is going to be a somewhat simple case. Assume that you are holding an object and maybe tied a rope on it. Okay, so this is the center. Right here is the center of the object, and it is attached to that blue rope, and the object is the red one. And it is, let's just say, maybe it is rotating along the circular path that direction. Okay, so my question is, again, I'm gonna apply F equals to MA. Okay, and I'm gonna say, since I'm focusing on where the object is, I'm just gonna say this is my x direction. I only care about the direction, which is along the rope, or because the rope is passing through the center of the circle. So the x is more important for me, but I'm gonna also put y-axis as well. Okay, so it's because it's two-dimensional forces. So since we want to figure out what is the net force, and that net force should be equal to the centripetal force, I'm focusing on the x-axis now. Okay, so what are the forces acting this object? So let's just show our free-body diagram. I'm gonna use, let's use green. There is weight force downward. That is along the negative y direction. And we have also the tension force, right, on the rope. And tension always a pull force. And it's gonna be this direction. So are there any other forces? And we are going to ignore drag, okay? Ignore air resistance or drag force. Unless it is given, we are going to ignore it for sure. So if you look at the free body diagram, which one is acting toward the center of the circle? Okay, and you can see that that's your tension force. And that's on the x direction, but I chose positive x to be to the right, so this is a negative tension. I want to make sure I write this T correctly, and that's equal to mass of the object. And what is the acceleration? Acceleration is also towards the center, and it's in the magnitude of v squared over r, but I chose the other way around as positive, so this is also negative v squared over r. So it would be better if I chose positive x to the left instead of to the right, pointing to the center. Then my force and my acceleration would be positive, but just because I chose the other way around, it did not change my equation at the end. So that would be tension equals to m v squared over r. So this is your centripetal force, okay? So centripetal force is nothing new. It is the net force towards the center of the circle. That's what I want you to understand. Okay, so let's clean up a little. Again, we will still ignore drag, and we are going to look at the cases. So let's just look at another case. Okay, so in this case, I'm not gonna tie it. Maybe the first case was like I was maybe rotating the object on top of my head or something. In this case, I'm gonna kind of rotate it, let's say this way. Okay, so it's attached to maybe this point, and now it's being rotated. Again, the rope line makes a cone. Okay, so maybe like it's again rotated this way, but the object follows a circular path. And let's just think about the free body diagram once again. So we have the weight force downward, and that's going to be the tension force along the rope line. So let's just make a clever choice this time and say that towards the center, right, is going to be my x direction, and upward is going to be my y direction. And maybe this angle here, I'm going to use the same line. This angle is in theta degrees, okay? I want you to see right now, this is also theta here, right? Because of that, like kind of looking like N, those corners are the same. Okay, so focusing on the free body diagram, again, I'm thinking about the object going through a circular path, and that circular path is happening along the x direction. So I'm going to focus on that, and I'm going to find out what is my net force along the x direction. In this case, it's not tension. It doesn't look like there's anything pointing directly to the center, towards the center, but the x component of tension does, right? So, and it is positive this time, so this is Tx equals to m. What is the acceleration? It is the centripetal acceleration, okay? So what is Tx? It is T. Since theta is not adjacent to the x component, it's going to be sine theta. That's equal to mv squared over r in this case. And this is your centripetal force in this case. Okay, so it's not one thing or the other. It could be multiple things. So you just need to figure out what it is. And in this problem, the y component of tension is going to be balancing out with the weight force. Okay. So for the third case, I kind of want to I showed an example or tried to explain it before. That was like a amusement park ride. So you're in a room, a circular room again. You just stand, like lean or just stand against the wall. And when the room is spinning, and you're going through a circular motion. So in that case, what you had was, I'm gonna put that circle maybe here this time. What you felt was the normal force. So something kind of is pushing you behind, yeah, right? And then you also have the weight force downward. You might have the friction upward if they're opening the floor or something, right? Then there's a there might be a friction related to that, or if the bottom of the surface is not open, then you have normal force instead of friction as well, because coming from the surface, not from the wall. So you would label them appropriately. I'm assuming that the bottom opens up, so there's a risk to fall. That means intended motion would be downward, then there would be friction. Assuming you're not falling, that would be static friction. I don't know if you're on the verge of moving, so I cannot say maximum static. I just can say that it's static friction. But what matters here is, again, in terms of centripetal force, is the, again, I'm going to call it x, and y is upward once again. So the centripetal force is, again, towards the center of the circle. So all I care for the centripetal force is the x-axis once again. And what force is along that axis? That's the normal force, right? And then we have mv squared over r. And what I'm saying is in this problem, it's the normal force. Sometimes it's multiple, like multiple forces are pointing that direction, and you just need to find the net force. So that's really important, that centripetal force is the net force towards the center. So it's not something you show in the Freiburg diagram. It is something that you find from the Freiburg diagram by looking at the direction of the center, okay, and maybe label that or as X or Y. And then when you apply second law along that direction, the left hand side, what you write as the forces, is your centripetal force. I hope that clears it up, and we are still continuing with other concepts next.